Hi. Okay. Hi, everyone. Welcome back to our next session for our next speaker. So it is my pleasure to introduce Professor Sotirios Saftaris. Is with the University of Edinburgh and the Institute of Digital Communications as a chair in machine learning and computer vision. He holds the Canon Medical Royal Academy of Engineering Research Chair in Healthcare AI. He's also a fellow of the Alan Turing Institute. His research interests are machine learning, deep learning, medical image analysis, image processing, and distributed computing. Core research application domains are computer vision, AI diagnosis in medicine, and computer vision in agriculture. Without further ado, it's my great pleasure to introduce Professor Sotirios Saftaris. The floor is yours. Thank you.
Hi, how are you? Hopefully, can you hear me okay?
Yes.
All right, let's hope that the internet will stay and the cicadas will be quiet. It's my great pleasure to be here today, and I hope you will enjoy this remote, at least in time for the time being, session. Unfortunately, I wasn't able to be there due to family circumstances, but I hope at least for the next 1 hour, you will allow me to go remotely through a journey about generalization. So thank you, Angelica, for the introduction, and also thank you, Juan and Carola, for putting this fantastic event together. I wish, as I said before, that I could be in Cambridge. So, as Angelica said, I'm Sotos. I work at the University of Edinburgh. And today I hope to take you through a story about the pursuit of generalization with real data as how we see it through my team. Just very briefly, so you better understand my accent. I'm Greek. I studied in Greece. And I moved to Chicago to do my PhD in electrical engineering and computer science. Then I moved for a while in Italy, where I led a new group working in machine learning. And then for the last 7 years or so, I am at the University of Edinburgh, where I lead a group where we do what I say, or at least what I like to call interdisciplinary AI, where we try to solve several issues of high societal challenges. The group is called VIOS. It means life in Greek. You might have seen it in the anglicized version. It's called BIOS, like with a B, but in Greek will be sound like VIOS. So it's a close-knit group between ourselves and Canon Medical, as well as other academics from other universities as well. So we work on a variety of themes, mostly around healthcare. I won't be able to talk about everything today, as obviously that would be, I think, highly boring. But we work in a variety of problems. For example, how can I learn about longitudinal effects using only cross-sectional data? How can we make imaging data? Or how can we deal with issues related to privacy? So we work also in the healthcare domain, but also in other settings. It's a computer vision, but also some work in general machine learning as well. So, but I think mostly here you are gathered because of your interest in healthcare, and indeed, I think one will be impressed by where we are today in the world. If you think about, we are definitely getting older, and this is not um, just thanks to like modern medicine. People are living longer and with more diseases and more than one disease at the same time. And despite all the progress that we've had, we still have killer diseases. Like for example, cardiovascular risk of cardiovascular death remains still high. There is, as you can imagine, these things, two things combined, they put a tremendous pressure into our healthcare systems, no matter where you're coming from in the world. So we still have to find mechanisms on how can we relieve pressure to the healthcare systems. So one such promise is held in AI, an AI that can help, for example, relieve tedious tasks from clinicians. Help, for example, diagnose disease faster or help start and identify anatomy and so on. And just, I mean, I think this slide is a bit ridiculous because it talks about deep learning and what deep learning is about. Uh, but it's mostly my opportunity to show beautiful pictures of cats and dogs. But deep learning essentially is a supervised learning technology. We provided with examples between, let's say, the input and output task. Here is a simple task of decision of cat and dog, but you can think of it as a classification of disease or segmentation tasks, and so on. So this is basically to say that we actually owe our current revolution towards the idea of being able to train these functions F that are very, very complex. Uh, but let's talk about developing AI in healthcare. So imagine a few years from now, you're finished with your PhD or you're done with your postdoc, and you say, I'm done with academia. I want to develop a startup, or I want to work for a startup that's going to develop AI for healthcare. So there are certain steps that you have to go through. First, you will have to pick a problem. Uh, and you will have to pick a problem that you know that you can probably market your solution. At the same time, because you're going to use an AI, you will have to find data to work on this problem. So you will have to work with different hospitals as a way to provide you data, and then with clinicians as a way to label them. If you're actually a good business person, you will probably do these three tasks simultaneously because it really depends. A good problem is the one that it's easy to find data, it's easy to, let's say, obtain annotations, while at the same time create a solution. And a solution that somebody needs, by the way, okay, and can use. Then, of course, you have to develop the model. And usually that's where we are in academia. Like we are probably around at the bottom part of this. Uh, and then once you've developed the model, you have to ask the very big question of like evaluation. How well will the model perform in patients that I haven't seen in the training set? So how well does the model generalize? Once you have packaged the model into a product, you will have to get it certified, and there are various routes for that. And then finally, you have to deploy it, whether it is within the NHS or any other healthcare provider anywhere in the world. This talk today is going to focus on this part. There's very complex, lots of discussions to be had. It's in a completely different talk about how do you pick a problem, how do you deploy, how do you certify, etc., etc., etc. But let's talk about this first. And how does the model generalize? And I will take a small parenthesis here and not talk about healthcare data and talk about tomatoes. They're not vegetables, they're fruits. But this is how we really, supermarkets have made us believe how tomatoes look like. They're like homogeneous all around. And that's how we really want to think about how data are homogeneous. Everybody's alike. In reality, that's not true. This is all the varieties of tomatoes that I was able to find through a very nice Reddit post on the internet. So, and actually, this is how we are as humans too. We are very different. So, if you think about it, we won't be able to have all the variation we have of how we would appear in the world in our training set. So, somehow, we must learn with less data and less variable data, but definitely we're not homogeneous. So there is some variation. So we must think of the origins of this variation and why is it there and how does it affect the data that we have. So let's talk about two things. First thing, if we're talking about medical imaging, there is going to be variation that comes from the device that we use to obtain the data. So if you are using an MRI scanner, the scan parameters, the actual scanner strength, the sequence used, all of this will affect how the image will look like. Okay? And in fact, here is the same type of sequence, the same type of strength, how anatomy of the heart would look from four different manufacturers of a scanner. So this is one part of the variation, and the other part of the variation is the what we are imaging, which is anatomy and pathology. So how we are as humans, like the population, our ethnicity, our gender, our age, the actual site where the data are. So if you think about the center hospitals are centers of excellence, so they will see certain patients distributions different than in a general hospital in a city. They might have different protocols as the way they process the data, pre-process the data, label the data, and so on. So all of these things affect how the data that we have vary and how our training sets will be and how our testing sets will be. Now, this variation maps into distribution shifts between variables. And there is also the map between shifts in a causal understanding. So there is a fantastic paper being written by Castro et al. On how and why causality matters in medical imaging. And within they map these origins of variation into types of different shifts that might happen from a causal understanding in terms of the tasks that we're trying to solve. So scanner shifts in general, the device shifts are called acquisition shifts typically, but the other ones they can map into annotation shift or prevalence or population shift and so on. Very, very illuminating example. Now you will wonder why do I talk to you about all of this? And I think I will tell you I want to talk to you about a very weird kind of variation that might happen, the variation that happens from spurious correlations, okay, and how that affects uh, basically anything that we do in machine learning in healthcare and our how it relates to building more robust algorithms, but also more privacy preserving algorithms. So let me show you an example from COVID just to get you motivated and about the discussion that's going to follow. So this is an x-ray of chest here and typically when we take the images, we will introduce a token basically that says left and right somewhere in the image. And this token is there to help, like, this is the left, the left shoulder. So now, let's say that, and this thing might happen frequently, so frequently will be placed. So it might happen that where it is and how it is, its direct may lead to the AI to rather than looking into the lung to detect, let's say, pneumonia, it might look at, oh, this particular token is looking like that. And oh, this means that I can, rather than looking at the lung for pneumonia, I will just look about how the token looks or where it is. So it might sound crazy, but these things have been documented. There's a very nice paper that actually documents all the cases of particularly how for COVID-19, rather than the AI reading the chest X-ray and looking at the lungs for pneumonia and other effects of COVID, is actually looking at tokens. So it's a spurious correlation between the token and the actual, let's say, outcome task, which is like detection of pneumonia or COVID. So this spurious correlation then becomes what we call a learning shortcut for the AI. So rather than solving the real task, it solves a parallel task. So now, let's think about a generic model for tasks. Again, we will have an image X, we will go to a task Y, and we will think of a training set with input and output pairs. And this is a very simplistic one. It's a classification task, but the same thing you can go for segmentation and so on. But we will talk about spurious correlations now. And the spurious correlations can be relating to the label Y, or they can relate to the input X. So within these two relationship, now I will introduce a taxonomy and I will walk you through how these things and offer you examples. So the taxonomy of spurious correlations, they can happen, let's say, correlated with the label Y. And I will talk about them about rare or very frequently that can happen. So let's talk about the rare ones. So sometimes within the medical images, the machine will imprint the name or some other characteristics about the patient. Usually as AI developers, somebody has gone before and pre-processed them and removed all of this. But sometimes things can sneak through and still will happen. In the bottom one, you will see an X-ray of a child and a parent holding their hands. You will see the classical left and right markers, as I hopefully you can see here and here. But also I have circled in red a tiny toy, which I think is a Peppa Pig. So the left and right markers are not the rare, is the Peppa Pig that is rare. So this is an example of real data as they happen in the wild. So there is a Peppa Pig there. And it has nothing to do with the hands. It's just it's correlated anywhere placed in the image. And but you can think about it if there is another image that might happen the Peppa Pig there. If somehow somebody had labeled this image to be, let's say, a right arm fracture, then it might solve the task of like, oh, if Peppa Pig there, right hand arm fracture. Frequently, you might have cases where there are hardware steering artifacts, or as I said before, the markers. But there can be also correlations with the image themselves. So, and ghosting artifacts due to, let's say, patient motion, or as you can see here, these are very common artifacts that are present that can, in fact, can create spurious correlation. Here is a patient where they have a rare anatomy, they have a prosthetic eye, and it looks completely different in the scan than the healthy non-prosthetic eye. And very interesting as well is this processing artifact. Sometimes you will pre-process data through, let's say, skull stripping, and here the algorithm half failed, so only the half brain has been skull stripped. So some of the data may have artifacts due to pre-processing failures. More frequently, you will have cases where, for example, where the patient and how the patient are positioned with respect to the field of view, the actual shoulder location and the patient position is a perfect actual shortcut that happens as a way to relate and detect than actually solving the hard task of reading anatomy. Or, the differences between, let's say, the scanners that I showed you before. And in the bottom, I have the PET images are completely two different sides. As you can see, here are spurious correlations, which is in this case intensity translated, and how the differences are between the two scanners. So what is the classical way of solving the generalization problem? And the classical way is, let's say, let's collect more data. The more data, all of these things should average out, right? That's what we eternally hope to do. But I don't think this is the scaling up solution. And as I'll show you later, actually, that's not the solution at all. We need to develop an AI that can better generalize to either the sensor variation or the population variation. Now, let's go back to the naive solution of let's put all the data together, and then we'll talk about why it doesn't work. So the naive solution is to pull the data together. And before I say about pooling, let's talk about environment, this term. An environment, we will call an environment a set of data from a source that will describe the same problem. Not necessarily the same task, but the same problem, say human anatomy. Or you can think about data from a hospital. The classical solution that we put by pooling the data is called empirical risk minimization. So we average over all the data over the loss. And the problem with this is that it will work well if your spurious correlation is present in the training set and in the testing set. Okay, but if the testing set that spurious correlation is not there, it won't work well. So it doesn't mean that it makes us robust to spurious correlation. It will only make us robust in behaving the same way if spurious correlation is present. The other thing is that if you think about pooling hospital data together, now it makes so every hospital may have its own spurious, either rare correlations or frequent correlations, spurious correlations. So by pulling them all together, you're exposing the model into more spurious correlations as well. But the last part is that makes rare data rarer. And this is a topic of a new project that we're starting in September about the influence and the validity and the importance of rare data as we develop AI models. But this is something that I just was useful to think that, everybody talks about a needle in a haystack, but what we're doing here, if the needle in the haystacks are where the value is, we're just basically increasing the haystack, but not amplifying the needle. Recently, Arajovsky proposed a new solution uh, to, to, to how we can better create generalization uh, motivated from a causal underpinning that is called invariant risk minimization. And it's rather complex theory, and I will try to simplify it a bit in words that, and I highlight some keywords here. So it says that knowing the environments and what might be different between them, find a representation that is either environment to the environment changes, or if you train an optimal classifier on top of this representation, the classifier will match its performance for all environments. The keywords here is knowing. So you have to know the environments and what might be different between them. And you also have to find a good representation that is invariant to these changes. Then solving for the optimal classifier, in some sense, it's easier. So I think IRM is an extremely cool theory, but it's actually really impractical. And I think you can see by what I bolded there, that the yellow there, that you need to know what changes. So, and and I think the theory showed also another paper showed that even in infinite number of environments, IRM can fail. And if you think about healthcare, the theory says that you hopefully capture all possible environments with all possible changes. But in reality, in healthcare, we don't really capture all of it. We only capture part of it. Um, Now, the final, I think, limitation of IRM is that you have to assume knowledge of the data generating process. And I think in healthcare, this is less easy than in other domains. And it correlates very well with the problem of causality. And a causal understanding about healthcare. So let me give you in few words what I mean by the data generation process. So let's think about, let's say that you have to take a picture of a car and you're building an autonomous driving solution. So there are some variables that control how the car looks like in the camera, right? So there is the shape of the car and the brand of the car and the color of the car and where it's placed in the road and where the sun is. So if you enumerate all of these variables that affect the scene, you have an idea of the data generation process. So at least you have an idea of all the variables that are at play. But it's not easy to do this for all the tasks in the world, and particularly learning the causal relationships between these variables. So after this first part of the introduction, let me introduce you about the rest of the talk that will be split in two parts, and it will deal with the two extremes, detecting the rare case, and then talk about how can we deal with some of the frequent correlations, as particularly they happen because of the different environments that we have. So, so let's talk about detecting rare spurious correlations. So let's revisit an example. This example of, let's say, names on an X-ray. Okay, so we have here, let's say, this weird X-ray image that writes a name there and an age, and we want to ask the question of something very simple. And now let me formulate the problem in a very simple setting, so it's easier to kind of like ground it a bit. So we will simplify it. Let's forget about the names for now. Let's forget about the age. And we will simplify the case where, let's say we have a training set. And in this training set, there is only one image that contains a spurious correlation. And this spurious correlation, this is one image. This is from the Zalando MNIST data set. And there is one image that contains the letter A. This is the letter A, an approximation for a full name. And it's just a simple thing to do, okay? We want to ask the question, can we detect in a black box setting that the spurious correlation exists in a single image of a data set that was used to train a model? So we have access to the model, and we ask the question, can we probe the model, and has the model learned a relationship with the letter A and the decision function, okay? And we want to do this in a black box setting. So this means we don't have access to the model, we only have access to its outputs. And in addition, we will assume that we don't have access to the data set itself. We only know that, let's say, if the data set is about Zalando MNIST, that any other data set will be fine as long as it doesn't follow within the domain of the Zalando MNIST. So, and our premise here is very simple, that if there is any sensitivity between the spurious correlation, it means that if I present the spurious correlation in any datum, the decision will somehow shift. The decision will somehow change. So if I have, let's say, 3 images here, one doesn't have the spurious correlation, one has the spurious correlation. We assume that we know the type of spurious correlation. We are relaxing now the extension of the paper. And then we have one other image, which is a control, where it has something that looks like the spurious correlation, but not exactly. It's a kind of, it looks like a patch, but it's not a letter. So the premise is that this image with the spurious correlation will slightly change the output more than and will be different from the outputs of the other two images. And actually, it says that the output of the change between output 2 and 1 will be bigger than the output 2, 3, and 1. So it's a simple metric. We do a statistical test here that checks how the output of a model changes when the spurious correlation is present. And the metric, if it's greater than 0, this means there is spurious correlation present in the training set. Although we don't actually see the training set, we only have access to the black box model. Or we have, or there is no correlation, spurious correlation present, less than 0 because it's negative. So, and I'll give you some sombering news, okay? So let me, first result here. So we have a training set, let's say there's a random MNIST. We take the training set, we take a random image out of the training set, and we introduce the spurious correlation. We will call this image with the spurious correlation on the canary, okay? Then we take this training set and train a model, okay? Then we train the model, then using our metric on another completely different data set, we introduce spurious correlations and we check our score. And we measure the score. And this score will have a value between, let's say, a negative and positive. Then we train another model and repeat, repeat, repeat. So you see in the x-axis there the different images, and the y-axis you see the score, and the variation that you see is the variation between the 100 different models that we trained with. So we are asking the question, if we train 100 different models on the same training set, can we detect memorization? And as you can see, the score really varies. So sometimes this kind of like spurious correlation, which is equivalent to this memorization here of the spurious correlation, um, is actually stochastic. It doesn't always happen. And it changes with the content of the image, although we don't know why yet. Then the reason why I call it memorization is because of the next result I'm going to show you. You might wonder, well, it's not really memorizing or learning the letter A. It's probably reacting to some features about the letter A. Well, that's not true. If I take and I do exactly the same thing, and during inference now, I just go and edit the letter A and remove a few pixels, the change of the score goes to complete negative. So this means that when the letter A is intact and is exactly the same as in the training set, the score is very high. But as soon as I remove some pixels, the score drops. So this means that it has actually fully memorized that exact spurious correlation. So it has the perfect relationship between the letter A and the decision function. So you might say, well, this means that you have too much capacity. You may want to regularize. You may want to introduce dropout. None of these things work. So whether you do dropout, batch normalization, or data augmentation doesn't help. And you might say, well, somehow you have overfitted and overlearned. Well, again, it doesn't help. Uh, Memorization happens very early on. So it seems that neural networks tend to exploit spurious correlations very early on the training set. So early stopping doesn't really help you here. So these are the bad news. The good news could be that, if you're a developer and you have access to the training set, um, you can actually have some mechanisms to detect where spurious correlation might happen, because we did find a correlation between spurious correlation and high influence examples. So high influence example means those examples that during the training, they introduce a large change in the training loss. So basically hard examples. So, you can learn an algorithm that looks for hard examples, and most likely if there is spurious correlation, it will be present, a rare spurious correlation, it will be present in one of these training examples. So this means that you can remove these examples and retrain, or if you have already trained a model, unlearn them, and you've done some work on that as well. Now, the other question is, where do we really, how do these networks learn these spurious correlations? Do they learn representations? How do these shortcuts happen? So we found that in a simple case here in an MLP, that there are, in the hidden layer, in the penultimate hidden layer, there is two unique nodes that they are correlated and related to the spurious patch of letter A. One encodes the actual content, A, and one encodes a location. So, and as you can see here, it lights up whether I have the letter A or something that looks a garbled letter A. So both of them like light up here, but here the random doesn't light up. So this means that we have learned a compact representation of that patch that will light up only if it's perfect with the letter A. So this means that if now you're a developer and you have white access, you can access to the model, you can prune the network to remove this type of spurious correlations after. Now, why do I worry about spurious correlations, as I mentioned to you before? And this is motivated by some work that we've done as part of an Innovate UK funded work, very large one, to put AI within the NHS. It's called ICARD. And the fundamental question there is, you have models being trained with NHS data. What is the likelihood that these models, when they're exported out, they have risks? Risks with respect to people being re-identified or leaking some information. And we found that actually these risks are not zero. Um, and and for example, the example with the letter A that I showed you, you can really think that if another letter A appears and the model has been trained with this type of spurious correlation, if that thing happens again, and now the model has been trained, rather than make a diagnosis on the basis of the content on the image, on the, let's say, the anatomy, will make a diagnosis on the basis of the letter, and that's a problem. So in this survey, we reviewed all cases of how models can be attacked during inference time. And I will highly suggest, if you're interested in this domain, to give it a look. Now, moving forward to the second part, and I think I should have another at least 20 minutes, um, I would like to talk to you about how can we design algorithms that are robust to this. And some of the solutions that I will show you rely mostly on better representations. So the kind of like gold standard way of thinking about robustness, when we have data from different, let's say, sources, where they're dealing with different tasks, or in general from different environments, it's called domain generalization. And I retrofitted this table from a very nice survey that I just found, that it compares how we deal with the problem of generalization. And it combines domain generalization with respect to test time training, domain adaptation, zero shot, and so on. And I will highly encourage you to give it a look at this paper. I found it very, very well put together and very interesting. But the way, at least in our team, we looked about achieving robustness, we think about it in two different settings. Setting of achieving robustness during training and during deployment. And during training, we always think about how can we let better representations that somehow uh, try to disentangle some of the information present in the data, and then how can we use synthetic data as a way to create diversity, create counterfactuals that correct for spurious correlations, or create diversity in the data as a way to augment, let's say, underrepresented groups and so on. So I'll hopefully in the next few minutes give you a summary of all of these. But let's start with a simple setting of thinking of, I would like to isolate the effects, let's say, of a scanner of from anatomy, of how the anatomy will appear in an image. The gold standard will be to have a patient that walks through a scanner and gets an image done, right? So and the best way to do this is to have the same patient walking through and going through all the scanners. But no real patient will do that. And this is the gold standard, and this is actually the IRM way in some sense. And you will have to repeat this for any effect that you want to isolate. I mean, it's clearly impossible to do that. So, but if you think about having a mechanism that can separate the influence of imaging from how the anatomy is, in that sense, whether the patient goes through a vendor A or vendor B doesn't make a difference. The anatomy is the same. The only thing that changes how the anatomy appears is on the image. So in that sense, if we are able to create a representation where we will separate the effects of different patients from the ways we capture different sensors on the image and the effects of the image of the sensor, then that would be very helpful. It will be helpful if you can think of taking the image and, you know, group the sensor characteristics together and group the patient specifics together. And this type of separation will work, can not only work in images, but can work in other domains as well, because you're separating and organizing these factors of variation, even in these two simple cases here as well. But it will work very well if you can only separate them very well. So the idea of these entangled representations is something that we've been working for in a while. Unfortunately, I don't have time to cover a lot of this today, but we just got a paper published that gives a tutorial and a full coverage of disentangled representations in the imaging domain. We have videos online as of the tutorials that we given in MICAI, and there is going to be a new workshop in MICAI in September, organized together with some colleagues from Germany. Now, how can this thing work? And I'll show you here an example of this very simple model where you take an image, and it's an autoencoder actually. You take an image, you split into learning two types of variables, one that encodes spatially where anatomy might be happening, and one that encodes some information about the scanner and the scanning characteristics uh, in a learnable way. And then by putting them together, you can reconstruct fully the input, but you can also attach different tasks as a way to segment, let's say, anatomy or do some predictions about with some regressors. The good thing is because here we can do multitask learning and we can reconstruct, this means we can learn in a self-supervised manner without any annotations. So indeed, we showed that with a fraction of labels, we can actually achieve very good performance. But the same model can do lots of things. It can learn by combining MRI and CT data. It can regress biomarkers as obtained by electronic healthcare records. We can exploit temporal relationships, let's say cine data, any, like let's say movies and videos. We can expand to include pathology factors, but also use the same model to do multiple inputs at the same time. So, but I won't bore you with this. There's lots of papers if you want to follow them through. But let's see how it affects this gold standard. So now, rather than having the patient to walk through all the scanners, we can actually simulate this in a very simple way. You can think of, I have, let's say, data from 3 different scanners. I can extract from each image the corresponding anatomical information and corresponding sensor information, and they will form groups because they will come from, let's say, different sensors. And now I can create and sample, because I have separated anatomy from the sensor variation. I can take a sample of the anatomy, I can take a sample from the sensor, and I create new synthetic virtual combinations. But the key here is this separation. So if the separation is not perfect, it won't work well, right? Because you're carrying essentially some correlation between the anatomy and the sensor, and you want to ideally disentangle them. So you can do this in two ways. One way is that we showed last year is that you can introduce a loss that says the following. So we do a trick here. We say we give data from 3 different scanners at the same time to the model during training, but the model only uses initially 2 and checks its performance on the third, and it does kind of like the roll around the table. And it checks the performance on the third one. If the performance is not good, of the model, it means that the representation was not good. So we go and penalize the representations and we improve how we better separate the representation of the imaging information from the anatomical one. And we showed, and in order to do this, we use meta-learning as a way to optimize this. But we were one of the first to, to deal with this problem in a semi-supervised setting, and it shows that it performs better than naive pooling. better than the random mixing as I showed you before, and much better than fully supervised meta-learning that doesn't have disentanglement. So all of these things combined work well. But if you have worked with meta-learning, you will know that it's actually pretty heavy. So we try to look for ways that we can improve this without creating complexity. And we thought of, and Shao came up with a new paper that's going to be presented in the next time that is called, it's compositional, uses VMF kernels. So the main idea here is that you take an image, X, and you say that will extract some features, and I will learn now in these features how to decompose them as a linear mix between some kernels that I need to learn that represent statistically the data. And this linear mixing and unmixing, so we do the learning and the composing as a way to learn again how the input data are. So you can do this without any supervision, but then you can have another task here that will relate to the task network. So just this process of linear mixing of these VMF kernels here allows you to somehow capture structure in the data and implicitly introduce a bottleneck and implicitly introduce some disentanglement. It's not pure disentanglement here. It's just an implicit one. But at the end of the day, it's enough that they create a lighter way of creating representations, creating this kind of like decompositions that align the data, whether they come from different hospitals. And it turns out that it's working very well, even in low show settings. But I don't want to give you everything, otherwise I will take Shao's thunder I will steal his thunder from the presentation in Unikai. Now, another difficult aspect about generalization is that thinking about, I talked to you about how we can generalize because of difference of the scanners, but what about the differences in anatomy? And difference in population. And this is actually a very, very hard thing. So if you think about, we will never have full coverage of all the population, right? So we will always have pockets in our samples of, let's say, normal anatomy or some other disease that we have. So but there is an unexplored part of the manifold. And if you think about in as mathematical tools, we perfectly know about interpolation, right? So if I give you any 2 points in the grid, you can draw a line between them. That line essentially interpolates between these 2 points. So somehow it would be nice to be able to do this within anatomical shapes. And of course, people have done this in the past. So if Paulina is in the audience and Alex, where they worked a lot on shape models and shape manifolds, they're able to do this type of interpolations. But if you think about trying to do this with variables like spatial tensors that you extracted out of the disentangled representations is much harder. But we still wanted to say, well, can we somehow create mix and matching some characteristics between two different, let's say, patients and create nice looking realistic data? So can we make a subject A that is normal, have some characteristics from a subject B that is now, and then makes this patient subject A abnormal. Now, um, we did this it's not a simple task, so we had to use a relaxation as a way to solve this, because we're talking about this binary tensor spaces that we cut and, let's say, remove one and replace it with another, and there's a lot of discontinuities, so you have to somehow introduce stochasticity as a way to relax it. But we were able to show that with the mechanism that we developed, that it's called the localized noise injection network, that we're able to show that we can still use it as a way to create realistic data that are useful and also adhere to the characteristics that we want. This idea of like content-based arithmetics, that's how we called it, like because of the anatomical content. It's actually useful as a way to correct for, let's say, prevalence shifts, to augment training sets, rare pathologies, uh, fix gender race imbalance, for example. But more interestingly, at least from a computer graphics perspective or a computer vision perspective, because we can actually edit the content space. We can actually bespoke now generate images. So image-based editing, I don't know if you heard of this before, in AI. It was one of the first that you're able to actually do this in a controlled. But all of these things rely, as of now, somehow the idea that the influence, let's say, of anatomy and the imaging is completely unrelated and completely independent. And even what you observe within the data set are all independent as effects. That's not true. As of now, all the questions that I showed you, they tend to ask fundamental, like what if questions, like how would the image look of a brain if, let's say, the patient was treated with X drug, or how would the heart of that patient look if they had this type of disease, or how would my brain look if I was 10 years older. So all of these type of questions are called counterfactuals. So in order to do proper counterfactuals, you need to have a proper causal model. And we wanted to ask the question, what is a good causal model, and is there any way we can introduce efficient causal models within generative mechanisms? And we're not the first, so there's others that done, let's say, with causal GANs or causal VAEs or causal normalizing flows, but we did it with diffusion models, which is a new breed of generative models that, for example, are powering now even GPT-3, OpenAI's DALI, and even Google's ImageGen. But I'm not going to go through the details, but I think what we did find, though, is very informative was when you create counterfactuals, there are certain things that you want to observe. And one is you want to create the right counterfactual for the right conditions of the input. So it's easy to create any brain uh, of any brain with an age 60, but you want to create my brain of age 60. And that's not an easy task. And this is something that we propose that as a way to measure as well. Now, this type of counterfactuals are not always useful, um, but you can also think the question in a different way, is that are all synthetic data equally useful? And are there some synthetic data that are more useful than others? So the same thing holds with augmentation in some sense. Like, do we always need to augment all the data or only some? And the, the the way we try to think about this is, let's say we have a classification task here between, let's say, some control and some, let's say, Alzheimer's disease patients, because we did this in the brain. So let's say this is the classifier, and we want to ask the question, does it really matter? Do we need to augment all these data points, or some are more useful than others? So I circle here in green one that I call a hard example. These hard examples are related to the high influence examples that I talked to you about before. Uh, and in some sense, maybe augmenting that one would be more useful than augmenting all the others. If you think about, I want to minimize how much augmentations I want to, or like how many counterfactuals I want to synthesize. So we set up here an adversarial task between a classifier, let's say a classifier that detects, let's say, Alzheimer's disease from non-Alzheimer's disease, and a generator that is able to take any image and generate for this image subject to a new age, some aged, the same brain aged. But this generator is fixed. The only thing that we play an adversarial game is between these parameters and the classifier. And we found that it works in augmenting with minimal samples in simple settings, better, for example, than just-time training, which is a very recent technique of simple um, augmentation on solving for um, for hard examples. Um, but also, we found that the same mechanism can correct for spurious correlation. That's how it connects to the rest of the presentation, where, so it's more likely uh, that you have to be older and have Alzheimer's disease. So we created a data set where this relationship was faked. So we flipped it. So we created that more young persons will have Alzheimer's disease than older ones, and the control will be more older. And as you can see, our method here was able to create counterfactuals that will correct for the spurious correlations as a way to improve the classification. Again, more details are in the paper. I think I should have about 5 minutes left, so maybe it's best I skip on the test time training aspect and give room for questions, if that's okay with you, and conclude now. But if more than happy to discuss test time training in the Q&A if you're interested. But let me kind of like wrap up a bit and think about kind of like start again with these motivating questions, right? So, you know, the healthcare pressures will not change. And I think collectively we can work together as a community, as a profession, as a way of thinking how AI can help resolve some of this. And I'm fully cognizant of the difficulties we have, right? So, you know, there is lots of other applications that rely on AI, and healthcare is one of the hardest ones, because the hardest ones in the sense that we will always have data that are harder to acquire, and we will never have enough data. It's much easier to collect data, for example, by driving a car around or playing a video game. And our annotations are costly. So if you want to think about generalization just by pulling data and collect more and more data, that's not gonna cut it, right? And generalization is the problem in AI, but I don't think there is a single solution to this. You know, I showed you examples of synthesis, and I didn't show you test time augmentation, test time training. I showed you, you know, augmentation. All of these things will help, but I think one of the interesting problems to work on will be how do we find the right solution for the right generalization task? And I think it's definitely something that's been uh, bugging me. And lastly, I mean, I don't think we should be working in a world where we don't understand what the AI does. And I'm not a huge proponent of black box with no understanding of variables. I'm definitely a supporter of representations. And I don't think the solution of disentanglement is the right solution either. Disentanglement has a very simplistic prior of independence, and that's not true. The factors are not uncorrelated, the factors of variation. There is correlation, there are relationships, there are causal dependencies, and somehow we need to go from, let's say, simple representations to understanding full causal concepts. Um, and with that, I think I should thank my team. So most of the work that you saw today is from John, Maria, uh, Pedro, Tian here, Gabriele, and Shao, and the early work was done by Agis. And thank my collaborators across the world in the UK, and the funders and yourselves for your patience, and the organizers for having me. Thank you very much for your time.
Thank you very much for the fantastic talk. So we have time for a few questions. Yes, please.
Thanks for speaking. I was curious about when you were like making images into other images. I was wondering whether there's any scope for like using topology kind of mathematical functions. So like, let's say you have a sine wave and like you stretch it, but it's still a sine wave. Like, could you have like a human wave and then you transform it, but it's still a human wave? And then you can
Yeah,
use that to get like different.
yeah, that's a fantastic question. Thank you very much. So there was a paper, I think last year, ICLR, that talk about disentanglement and its relation to topology. Um, I must admit, when it goes into topology and the whole mathematical interpretation of it, and I, I, my IQ on this is very low. I definitely believe the I definitely believe there is a connection, and I hope somebody finds it and somebody exploits it. I don't think I have the depth for it. Or I find one of the brilliant students, I have many that maybe are keen to explore it further. Um, but there is a definite relationship, according, if I believe to this paper, of between disentanglement and how you manipulate certain variables and the topology of those variables.
Thank you.
Sorry, it was not very informative, but at least it was honest.
We have more questions. So, okay, yeah, okay.
Thank you for the talk. There's a moment when you're discussing, the generalizability for different, different machinery and different things. I was wondering if maybe there was a mechanism for better explainability that may, if you constrain your model in a way that it's explainable, really explainable, to the point that actually you wouldn't have that issue with the different equipment and hardware. And I wanted to know if you had any perspective on that, if there was like a mechanism maybe where you could justify your network predictions in a way that would be robust to that.
Yeah, that's a fantastic link actually. So that's a perfect question. Um, there is a definite correlation between explainability and generalization. Explainability, if you think about it, is a bottleneck, right? So you're reducing the space of where your functions would lie as a way for seeking a decision. So if you, and in that sense, uh, you're creating a bottleneck, and you should somehow be more robust and be able to generalize well, just because you're forcing the model to not seek any possible function but the one that is explainable. There is, though, a question to be had or to be made about, does explainability avoid spurious correlations? And that's an interesting point. I haven't thought about that. Like thinking of the example of the letter A of this rare spurious correlation, or the Peppa Pig. Um, would that, if you have a model that is explainable, will reduce that? And I think to better answer this, we need to take a step back and think about the data generation process and the causal understanding. So if you think about generative learning, or the generative way to, let's say, decision making, it means that I have fully extracted all the variables of the model, and then to make the decision, I rely only on few. Versus the discriminative one, it throws away all the information is not necessary, useful for the task, if you believe in information bottleneck. So in that sense, if you have learned the right set of variables that explain the data and explain everything in the data, if you reduce that set of variables to be the minimal ones that shouldn't include the spurious correlation, then hopefully that will solve also that problem. But finding the minimal set of variables in a is I don't think it's an easy problem to solve, but definitely um, it's definitely a good direction.
Okay, thank you. So I have a question actually. So, well, first of all, thank you very much for your great talk. And I'm wondering, toward the second part of your talk, one of the key words that I hear often, it was augmentation. And actually in one of your slides, you said, okay, do we need to augment all samples? Because it's clear that sometimes you might affect your semantics. So I'm wondering, you mentioned hard examples. If you find it manually, because there is an area that is automatic data augmentation. So you search in all the space of possible solutions on your augmenters, and you choose that automatically, such that the semantics or the augmenters that you choose are not going to affect your semantics. So have you used any automatic search on that, on the space?
Yeah, so we haven't done automatic augmentation because Sorry, one of the phones. We haven't used automatic augmentation for finding what is the right augmentation for the right sample to do. It shouldn't be difficult. I know that one of our co-authors, Chenchin and our collaborators, has a paper that used that automatic augmentation to do as a way to find the right augmentation. I think the right question to the right direction here is not just necessarily what is the right augmentation, what is the right sample to augment. And I think this is where that paper was trying to go to. That is not only the right mechanism, but also which sample to augment. Like, do we really need to be flooding with extra data, everything? Because in that sense, if there is some spurious correlation that happens frequently, by augmenting them, then you increase its frequency, you increasing it, right? So this was kind of like trying to motivate us behind that question as well. So do we need to augment everything or augment the right things?
But the augmentation is not related about the selection of the sample, because when you look in the search of possible solutions, you will find that a particular sample might not be relevant because of that might affect the semantics of your output. So that will be connected with which sample actually might be relevant.
Oh, I see your point. I see your point. Yeah, I see your point. You assume that you can apply. Yeah, in that sense, if you do that search, yeah, if you assume the semantics only, yes.
Yeah.
Sure.
Thank you. Do we have more questions in the audience or Zoom? If no, actually we are on time. Thank you very much for the fantastic talk.
Thank you, everybody. It's good to see you. And I'm sorry I couldn't be there in Cambridge, and I hope you have a good rest day of the conference. Bye. Thank you for having me again.
Thank you.